everything that has to do with interactions and Dirac fermions. And this didn't change with the advent of twisted bilayer graphene, which is kind of one of the hottest topics, where Oskar, around these days, where Oskar proposed the first strong coupling theory, which is of twisted bilayer graphene, which is kind of right now, well, in my view, one of the most accepted ways of looking at this problem. And today he's going to be talking about a new method of looking at Hofstadter spectra, strongly interacting Hofstadter spectra that can be applied in graphene and hopefully in twisted bilayer graphene and hopefully other systems. Thank you.
Okay, thank you so much, Andrei. Thank you very much to everyone for coming. This is my first time in this beautiful place. And thank you all for the hospitality here. So, as Andrei said, I will talk about the interacting Hofstadter spectrum and strong coupling of twisted bilayer graphene. I will hopefully define all of these terms as we go along. And although this talk is targeted for the twisted bilayer graphene, I think the method that we found to solve this problem is actually more general and could be of interest to people in the audience who are not necessarily working on the twisted bilayer graphene. So I've been very fortunate to collaborate with Xiaoyi Wang, for which the second part of this talk, the main part of the talk, is about. And but before I get to the second part of the talk, we will discuss the effects of magnetic field. In the presence of interactions for the narrow band, I need to set up the motivation, and that will be done in the first third of a talk or so. And so the first part of the talk will be a zero external magnetic field, and it will deal specifically with the narrow bands of twisted bilayer graphene. But as you will see, at this point, the method that we will use to solve that problem is actually more general than just looking at the twisted bilayer graphene problem. So in the first part, I will think about these narrow bands that I'm sure many of you have heard about in the presence of strong interactions. And the remarkable thing is that unlike in the Hubbard model, where in strong coupling, if you were to add one particle or one hole to this problem, and that hole or particle would not disperse, in this case, because the narrow bands are topologically non-trivial, the Wannier states have more complicated overlaps in the Coulomb interaction, including, for example, assisted hopping terms, pair hopping terms, etc. And such terms are actually able to delocalize the excitation. So even in the case where we neglect the bandwidth of the narrow band, simply by projecting the Coulomb interaction onto the wave functions of the narrow band, and then exciting on top of a ground state by, let's say, one particle or one hole, that one particle or that one hole can disperse. And so that's the problem we want to look at in the first part. And then the natural question is, if that's true, if we apply an external magnetic field, will this dispersion get Landau quantized? And how would we solve that problem? So we start with the continuum model, where we have which is a 4x4 differential Hamiltonian. The first block here is a 2x2 matrix, which describes the Dirac massless Dirac particles with the velocity set by the Fermi velocity Vf. The top layer and the bottom layer are rotated relative to each other by the angle theta, and they're coupled to leading order in the continuum theory by this coupling matrix, which is position dependent, and it contains two terms, two parameters. One is the interlayer tunneling through the so-called AA region in the spectrum. So when we twist the bilayer, there are regions where are predominantly AA stacked. And we're going to denote this one by W0. And in addition to that, there is a coupling through the AB regions, which we denote by W1. And these two parameters in the rigid twist situation would be equal to each other. But if there is a relaxation, which there is, and the AA regions shrink relative to the AB regions, then the values of these couplings are different, and the W1 would be somewhat larger than W0. But the order of magnitude for this is about 100 MeV or so. Okay. Now, if we're to neglect the small angular rotation of the Pauli matrix, then this effective Hamiltonian, including the interlayer tunneling, which knows about the twist angle through these tiny little wave vectors Q0, Q1, and Q2, which are set themselves by the angle. But if we were to neglect this part, this Hamiltonian will enjoy a perfect particle-Hall symmetry, which was shown in this very nice paper by Andrei and collaborators and by Leon Balance's group and collaborators. Neglecting this small angular rotation doesn't mean we neglect the twist. The twist mainly comes through this interlayer tunneling term. So in fact, the error that you make in this particular case at the level of wave functions, as Andrei groups has shown, is just as big as if you neglected spin-on recoupling in graphene. So this is relatively minor approximation. And for some of the things that I will mention, we will make that approximation, simply because then this perfect particle-Hall symmetry helps us solve some of the strong coupling problem a little bit easier. All right. So now imagine that we solve the Bissell-McDonald model, this continuum model, and then we get a bunch of bands. There are many, of course, of them, because the spectrum of the Dirac cone gets folded. We have a new length scale in the problem. That length scale is the moiré period. The moiré period is about 13 nanometers at the first magic angle. Of course, the atomic distance between the carbon atoms is about 1.5 angstroms or so. So that's a much longer period. And therefore, we fold the Brillouin zone many times. And as we fold it, we create new bands. And what's interesting about this problem is that very near the charge neutrality point for these special twist angles, there is a relatively narrow isolated pair of bands per valley per spin. And of course, the famous experiments by the MIT group and then followed by others have discovered strongly correlated states when these narrow bands are partially filled, and these correlated states include superconductivity. Now, what we would like to do is we would like to write a theory in which we integrate out in the renormalization group sense all of these remote bands and find the effective Hamiltonian just for the electrons which live in these narrow bands. That's easier said than done, but it turns out that this program can actually be accomplished. The details are in this paper, and it goes via 2 stages. In stage 1, which is defined as the energy scale above of the order of the interlayer tunneling, so few W1s, we integrate out all of these remote bands actually analytically. And we can do that because in this window, both the Coulomb interaction and the interlayer tunneling are perturbative. The energy is much larger than W1, and so all of your denominators have this large energy scale in them. And so we are able to, therefore, integrate out thousands of bands without this costing us too much numerically. Now, there is an energy scale, as I mentioned, which we call EC star here, below which the effect of the interlayer tunneling becomes non-perturbative. And at this point, we have to take seriously the fact that the periodic potential due to the moiré creates subbands. We cannot treat it perturbatively, but we can still treat Coulomb interaction perturbatively here because we are protected by this gap to the narrow bands. So at this stage, which has, let's say, about 20 or 40 bands above the narrow band, we can simply perform Wilsonian RG by integrating out one band from above, one band from below, renormalizing the self-energy, re-diagonalize the new problem, integrate out the next pair of bands until we are left just in this narrow band. And we can do that perturbatively in the Coulomb interaction, but non-perturbatively in the Ws. And this is numerically not a big problem because we're dealing with about 20 to 40 bands. Now, it is very important to show that this energy scale, which is not sharply defined, does not change the result that we get over here, because we could have stopped the flow in the first stage a little bit earlier and do the numerical calculation with the isolated band removal with more bands. as long as the stage one is under control, the answer will have to be the same as if we stop this a little bit later. And we demonstrate this in this paper. So this intermediate scale, the auxiliary scale, actually does not show up in the problem. Anyway, the upshot of this story is that the effective interaction Hamiltonian, the Coulomb part of the interaction, now projected onto the narrow bands, take this form where delta rho is the projected density operator minus the background density. And these psi's here are the exact renormalized wave functions of the narrow bands, for which the effect of the remote bands has already been included. And then in addition to this quartic term in the problem, we also have the renormalized kinetic energy, which is quadratic and does not fit into this form. Notice this is not normal ordered, which would be actually useful for us. And what we find is that this is small compared to this. In fact, these renormalized kinetic energy terms are not that much larger than the bare continuum model bandwidth. So now, at this point, because the Coulomb interaction within the narrow bands, renormalized narrow bands, is much larger than the kinetic energy, we would like to solve this problem first, the way we would do it in strong coupling of a Hubbard model, and then treat this as a perturbation. Now, the difference between this problem and the usual Hubbard model is, of course, that the wave functions of the narrow bands, they're not simply nice localized Wannier states on each site, but they have a more complicated character, and that makes this part more interesting. Now, there are certain exact statements that can be made about this strong coupling case. The first is that if we confine ourselves to the charge neutrality point and solve this problem by itself, then any many-body state, which is annihilated by this quadratic operator delta rho, is a ground state. And that's because the projected Coulomb interaction is still positive semi-definite. So if this is a positive semi-definite operator and you find a state which is annihilated by it, you found a ground state. Now, if we go away from the charge neutrality point to even integer filling, then one can find eigenstates of this projected density fluctuation operator. And as was shown in this very nice work by Andrei's group, these states are not only eigenstates of this Hamiltonian, but for a rather wide range of parameters, they're also the ground states. And so again, basically states which are completely filled for particular combination of the narrow band wave functions and which are eigenstates of this Hamiltonian turn out to be also ground states. I will discuss their physical character in just a second. And then finally, if we're at odd integer filling, it's a little bit harder to solve this problem exactly. But if we are in the so-called chiral limit, where the sublattice is perfectly polarized, then one can show that Chern states and their relatives are also eigenstates of this projected density operator, and numerically over a range of parameters are also the ground states. They're not always the ground states if the W0 and W1 are close to the realistic parameters, but there's a range of parameters close to the chiral limit where these Chern states are exact ground states. So this is the analog of what would happen in the Hubbard model if you neglected the hopping T and only took the Hubbard U, which in this case is much more complicated because we have to worry about the wave function sitting in this projected density operator. And then just simply solving the problem at integer filling. Now, the upshot of the story is that generalized spin valley ferromagnets, and of course their Chern relatives and intervalley coherent states, are favored by such projected Coulomb interactions. And there is a body of literature now for this, which establishes this. Now, what I'd like to do at this point is to talk about what would happen if we add a particle or hole to such states. As I said, this problem would be trivial in the Hubbard model, because if we neglect the hopping T, and we just have a density in a Hubbard model, fine, we can solve the problem at integer filling, but if we now add an electron or hole to it, it's not going to disperse. It's just going to sit there with an infinite mass. But in this case, because of the non-trivial wave functions, that electron or then hole will disperse. So how do we solve that problem? It turns out that that problem can also be solved exactly. The key idea is that imagine that omega is a state which is annihilated by the projected density operator delta rho. if we take the projected Coulomb interaction and act on a state, omega, onto which we then create either a particle or a hole, so X could be either a creation operator or an annihilation operator, then, because every delta rho acting on omega gives us 0, we can replace this product that we would nominally get with the commutators. And therefore, the operator count on the right-hand side of this equation, if the projected density is, let's say, 1 creation, 1 annihilation, let's say X is 1 creation, the operator count will not change. We will still only have 1 creation operator after the first commutator. But the same is true after the second commutator, which means that what we get on the right-hand side is simply 1 creation operator delocalized a little bit. And so we can just Fourier transform that and find the operator eigenequation, which is not a many-body problem. It's basically a one-body problem, and then solve this problem. And this can be done exactly. Now, the interesting thing is that if we start with one of these ground states at the charge neutrality point, and we were to add, let's say, electron or a hole, there's a gap. That's not surprising because we have a Coulomb interaction. Just like you have a Hubbard U, there's a gap to putting in an electron. But as I mentioned, and that gap is set by the Coulomb scale, where the epsilon here is the dielectric constant of the medium in which the twisted bilayer graphene is placed, and Lm is the period of the Moiré length scale. So the Coulomb interaction, typical scale of the Coulomb interaction is set by this, depending on screening, etc. This is 10 to 15 millielectron volts. So that would be the gap at this point. But notice that the excitation disperses. And the bandwidth of the dispersion is comparable to the gap itself. So this is unlike in a Hubbard model. And this all is happening because of these assisted hopping terms, pair hopping terms, etc., which in this case will be included exactly. So this is very interesting because we have itinerary C, which emerges because of the non-trivial nature of these narrow bands, even at strong coupling. This, as I mentioned, this would not happen in a Hubbard model. In a Hubbard model, the bandwidth that you would get would have to come entirely from the hopping T, from the bandwidth. So the natural question then is, if we stop at this order in the expansion, because the kinetic energy now is going to be small compared to this in the strong coupling limit, what would happen if we applied an external magnetic field? Will these excitations, whose bandwidth is set by Coulomb, Landau quantize? And if they do, how? And how would we do this calculation? That's the main motivation of this talk. Now, I mentioned how this would work at charge neutrality point, but in fact, this trick can be used at the even integer filling as well, because the only thing that we really needed is not necessarily that the eigenstate is annihilated by the projected density operator, but in fact, it's enough for it to be an eigenstate of the projected density operator. There's an additional term that one has to add, but other than that, the argument goes through. Once Fourier transforms, this would look like an exchange term from the Coulomb interaction. And this part will look like a Hartree term. This Hartree term will have a sign that will be different whether our creation or whether our X operator is creating a hole or creating an electron. There will be a difference in a sign, and that will be actually important. So in the previous example, where we were at charge neutrality point, this would be the dispersion of both the electron and a hole. They would be the same. But if we are away from the charge neutrality point, we will get a different dispersion for the electron and a hole. So let's say if we are at mu equal to 2 and we put an electron into the problem, that dispersion will not match the dispersion of the hole. So in this case, we are showing the strong coupling single particle excitation spectra at every integer filling, assuming we are in this chiral limit, where I mentioned that we can find the exact eigenstates even at odd integer filling. The results change somewhat if we move away from the chiral limit, but not that much. So the main point goes through. So this is the charge neutrality point. The excitation for the electron and for the hole, both of them are gapped. These are all Coulomb units, and they look like this. There's a minimum at gamma. Remember, the continuum Hamiltonian has 2 Dirac points at k and k prime, and the gamma point has 1 maximum and 1 minimum. Once you turn on Coulomb interactions, as long as they dominate this bandwidth, the band looks completely different. you have a minimum at gamma, and then there is a flat portion between m and k. Now, if we go to nu equal to 1, remarkably, the two terms that I mentioned for the whole cancel out, and they cancel out almost exactly. So if we were to add a whole, yes, there's a gap to it, but it's almost completely non-dispersive. So these holes will be very heavy, and you would have a hard time seeing them in quantum oscillations because, of course, the Landau levels will be very, very close together. On the other hand, if we were to add a particle at nu equal to 1, so we move away from the charge neutrality point, then these two terms add, and the dispersion more or less doubles in its width. Okay, so the excitations at mu equal to 1, as long as they move the filling away from the charge neutrality point, will come in as light particles, and you should see Landau fans coming out of that filling away from the charge neutrality point. If we now go to nu equal to 2, then this term is doubled compared to nu equal to 1, and the dispersion is even wider. And in this case, the whole dispersion gets flipped. So again, the low energy excitations will not go to the gamma point, but they will go to the part of the spectrum which is flat. So again, you will have a heavy hole while you have light electrons at nu equal to 2. It gets reversed for the negative fillings. So again, excitations which will move the filling away from the charge neutrality point will be dispersing. The excitations which move the filling towards the charge neutrality point, they have a large mass. And a similar thing happens at nu equal to 3. We can, of course, do this calculation at nu equal to 4 as well, including the kinetic energy. So as you see, this asymmetry therefore creates light fermions on one side of the integers, and then heavy fermions on the opposite, closer to the charge neutrality point side of the integer fillings. Now, to illustrate the effect of the Coulomb interactions on the dispersion, let us actually completely empty the band. And in this case, we can solve the problem including the kinetic energy exactly. And what we're going to do in this little simulation is change the strength of the Coulomb interaction. So this form in the momentum space for the Coulomb interaction is for a situation where we have two gates sandwiching the twisted bilayer graphene at a distance xc. So we solve the continuum Hamiltonian, and when this dielectric constant is very, very large, we just get the usual bands. They're not actually that narrow because we are not at the magic angle. But we have a maximum at the gamma point for one of the bands per valley per spin and a minimum for the other. But now we start decreasing this value of the epsilon, holding the kinetic energy fixed, and then look at these excitations. Basically, this term is going to grow as we decrease epsilon. And as you see, this excitation starts flattening and gets heavier. And at some point, when the Coulomb interaction is strong enough, it will invert this dispersion, and we will get a heavy electron. So again, doping towards the charge neutrality point, we would not expect strong Landau fans to show up, and this is indeed seen in the experiments. All right, so that's the motivation. We understood this at some point about 2 years ago or so, and we wanted to understand what would happen if we now place this problem in an external magnetic field. The Coulomb interactions dominate, and will these spectra get Landau quantized, and if so, how? And how would we do this calculation? So this work was done in collaboration with Xiaoyu Wang, who is a Dirac Fellow at the National High Magnetic Field Lab, and who's done most of the numerical calculations that I will show you. So we are not the first ones to solve the problem of the continuum Hamiltonian in the presence of an external magnetic field. The non-interacting problem has been solved 10, 11 years ago. And the spectrum at the magic angle would look something like this. This is the non-interacting problem. This is the narrow band. This narrow band, of course, gets broken up into Hofstadter subbands. There's a gap to the remote bands, and the remote bands themselves get broken up into Landau levels, or if you wish, Hofstadter subbands. But we would like to solve the problem in the presence of strong Coulomb interactions, and this was not done before. So what we need to do is we need to project now onto the Hilbert space of the Hamiltonian at finite external magnetic field. So we need these wave functions, project the Coulomb interactions with these wave functions, and then use this double commutator trick to compute the spectrum. That's the idea. Now, the way the problem is solved previously, mostly, is to solve this problem, with Landau levels. In other words, you take the continuum Hamiltonian, which I showed you, you minimum substitute the vector potential, and then you use the ordinary Landau level basis to set up a giant matrix, and then you diagonalize this matrix. In order for this to converge, the upper cutoff on this matrix has to be about 25 times, actually it's 50 times the number of levels in here. So if there are two Q states, let me just clarify. So if there are two Q states here per valley per spin, then one needs 25 times Q Landau levels to converge. So what does this mean? It means that you carry gigantic amount of information about these remote bands and how they're Landau quantized, just so that at the end of the calculation, you can throw them all away and only use these wave functions to the projected Coulomb interaction. And that prohibits calculating the Strongcoupling problem, in particular at low fields, or if you want to go near a simple fraction like 1/2. At 1/2, that's not a problem. But if you want to go very close to 1/2, it's also not very efficient way to solve this problem. So as I said, one option would be to solve this problem in the Landau level basis. But this is problematic because at low magnetic field and near simple fractions of the flux, we have a high number of Landau levels that are needed to be kept in order for this non-interacting problem to converge. So we need a new method that would work even if the narrow bands are topological at b equal to 0. So if we had a Hubbard model problem, we would know how to do this. We would do a parallel substitution for every hopping in T, and we would solve that Hofstadter problem. But in this case, we can't quite do that because we don't really have good Wannierization of this. You know, there are these fidget spinner wave functions, and that gets a little bit tricky, in particular if you want to represent all the symmetries of the zero field narrow bands locally. So the idea is to use the so-called hybrid Wannier states at zero magnetic field. So let me first introduce this. So we're going to solve now the zero field problem, and then use the insight from the solution of the zero field problem to say something about a finite field problem without ever touching the Landau levels. So we're never going to use Landau levels to solve this problem. We're only going to use Wannier states and magnetic translation group. So at b equal to 0, let us consider this, which I'm sure is well known to many of you in the audience. This is the idea that was presented in this very nice paper by Andrei collaborators. We have a projection operator onto the bands of interest, which in our case, those are the two narrow bands per spin and valley. And then something which is analogous to a periodic position operator. So in this particular case, we choose this delta Q to be something very, very small and pointing in this direction. And we would like to diagonalize, we would like to find the eigenstates of this Hamiltonian, of this operator. Okay, so because the position is projected along this direction, we will get a good quantum number that corresponds to the translation or corresponds to this momentum, G2. So for every K, which is along G2, we will get the eigenstates and eigenvalues of this Hamiltonian, and we can study this as a function of K. It's the famous Wilson loops. So we admix the Bloch states along this path. I'm sure this method is well known. We have to compute the overlaps of the zero field Bloch functions. And at the end of the day, the eigenvalues, or at the end of the day, this operator, which is the Wilson loop operator, will have eigenvalues which can be put into this form. Sigma 2 is a 2x2 matrix with minus I and I on the off diagonals, and its eigenvalue can be thought of as a expectation value of the position along the localized direction, which the eigenstates of this Hamiltonian will be in one direction because we are mixing Bloch states in this direction, rescaled by the moiré wavelength LM. So because we have two narrow bands per spin and valley, we're going to get two eigenvalues of this. So these Wilson loops, they look like this. If we focus for a moment on the chiral limit, when the ratio between the two tunnelings is set to 0, we find two eigenvalues because we have two bands. And one of them moves to the left as we increase the good quantum number k, the way a Landau level in the Landau gauge would, while the other one moves to the right, as if we had a Landau level in the opposite magnetic field. Now you see, if you change the value of the ratio between the AA tunneling and the AB tunneling, this overall topology does not change. You still wind by 1. And so when you increase this good quantum number from here to here, your localized states will change its expected position by 1 unit cell, either to the left or to the right, depending on which of these two bands you have. But of course, while the topology does not change, the actual shape of these Wilson loops does. And the closer we come to the realistic value, which is probably, well, either here or somewhere between maybe these two values, the flatter this part gets. But eventually the system knows that it's topological and then it drifts. All right, so the idea is to look at the eigenstates of this operator. These are, of course, well-known eigenvalues, but we're going to look at the eigenstates. So as I mentioned, we expect the eigenstates of this operator to be localized in one direction, but they will be Bloch extended in the direction that's associated with this good quantum number k. So they will be like Landau gauge Landau levels, almost, except not quite. So the 4 plots here on the left are showing one of these hybrid Wannier states, which is centered at the home unit cell at the origin. So the first 0 means it's the first unit cell, and the second 0 means that the good quantum number k is set to 0 for this particular case. So as we move along this direction, we are at the origin. And indeed, we see that the hybrid Wannier states are localized, and this is decomposed per layers and per sublattice. So this is top A, top B, bottom A, bottom B. Most of the weight in this particular case is actually on the B sublattice, but there's some weight, of course, on the A sublattice as well. In either case, we see localization in one of the directions, but then we see Bloch, that these are Bloch extended states in the other direction. Now, as we keep the index of the unit cell fixed, so the first index is still 0, but now we increase k, so we move along this good quantum number, these states will change their expected position. But you see, so indeed, while this would be somewhere in the middle between these two columns, here would be on this column. So indeed, the center is drifting, but the distribution is much more non-trivial. It's not just a Gaussian, as one would get with the Landau gauge, Landau levels. These are the famous AA stacking regions where most of the electrons like to live. So that's how that Wilson loop is drifting. The distributions look something like this. All right, so now here's the key insight to solve the problem at finite field. Imagine we take the hybrid Wannier state, which is centered at the origin, or it can be near the origin. It doesn't have to be exactly in the home unit cell, but let's start with the home unit cell. And now we're going to judiciously choose the vector potential for the finite field problem to be in this Landau gauge such that it is translationally invariant by translations in this y direction, which is precisely the direction in which our hybrid Wannier states behave like Bloch states. So these symmetries will nicely match. Now, of course, this vector potential is large as we move far away to the right and far away to the left. And so that's the reason why we cannot treat the vector potential perturbatively in general. If you have an extended state, you can't do that. But if we take this particular hybrid Wannier state, which is centered on the home unit cell, then as long as magnetic field is not too large, the expectation value of the Hamiltonian at finite field with the zero field hybrid Wannier states centered at the origin will be very close to that expectation value at zero field, because the corrections will come from first and second moment, let's say in the Dirac case, first moment of the position operator, but that's small in this hybrid Wannier state because it's localized in this direction. So this polynomial gets cut off by the exponential. And so that means that this state cannot be too far away from being a linear combination of the finite field narrow band Hofstadter states. Because if its expectation value of the Hamiltonian or Hamiltonian squared was large, then of course we have to be far away. We have to be admixing states which are from the remote bands. But at small field, we are guaranteed that this will not happen. Okay, so what does this buy us? If we have one state for which this expectation value happens to be small, and this one state happens to be, therefore, a superposition mostly of states from the finite field narrow bands, then we can use the entire, we can use the magnetic translation group irreducible representations to get the entire basis at finite field from the zero field basis. Okay. So we, again, judiciously use the translation symmetry of our hybrid Wannier states in this direction, choose the Landau gauge such that it increases in this direction, where our states are exponentially localized, and then argue that this state must be a superposition mostly of the states from the finite field narrow band. And that allows us to avoid using Landau levels, using all the Hofstadter bands that we get from the remote bands. It will zoom in directly to the narrow bands. Okay, so, and as I said, again, if we project now this state onto the representations of the magnetic translation group, we can generate the basis that we can then use to solve the finite field Hamiltonian. All right, so what is the symmetry of the problem at finite field? If we, so we need to define two operators. One of them is just simply a translation along L2. And remember, this is a good symmetry even for the finite field problem, as it was at zero field problem, because of the judicious choice of the gauge. On the other hand, if we translate along the L1 direction, then we have to accompany such translation by a gauge transformation. And that's a symmetry of the finite field problem. Now, so we have two operators which commute with the Hamiltonian, but in general, they will not commute with each other. So consider a ratio of the total flux through the unit cell to the flux quantum to be some fraction which is relatively prime p over q. So we're gonna confine ourselves to these fractions, but we can solve it for any fraction if you wish. So for example, if p is 1 and q is large, that corresponds to low field. But p doesn't have to be 1. Then in that case, both the translation along the L2 direction will commute with the Hamiltonian, but so will the translation along the L1 direction, the magnetic translation along the L1 direction. But of course, these two will not commute with each other. However, if we raise the translation along the L2 direction to power q, where q is defined through the flux, then these two will also commute, which means that we can find simultaneous eigenstates of these two operators. So the idea is to take our zero field hybrid Wannier states, and not here now represents which 1D unit cell we localize it along. So in the example that I was giving you, this n naught would be 0. But we're going to allow this, for example, to be also 1, to be a little bit to the right or a little bit to the left, because again, these are localized states. So the effect of the magnetic field, as long as it's not too large, cannot be too large on such states. And then, of course, there's a good quantum number K2, which is along the G2 direction. And then this is just a simple projector onto a representation of the magnetic translation group. So if we act with TL1 on this resulting state, it is clearly an eigenstate because you can shift the sum over S by 1, and you will pick up an eigenvalue e to the 2 pi, e to the minus 2 pi I K1. So this state will be an eigenstate of TL1 by construction. But because TL2 to power q commutes with every TL1, it will go through and it will hit our zero field hybrid Wannier state, but that's also an eigenstate of TL2 because it's just a Bloch state. And so that means that this is also an eigenstate of TL2 to power q. So we can label this state, which we obtain simply by projecting the zero field hybrid Wannier state in the the home unit cell or the close to home unit cell by two quantum numbers, K1 and K2. And these two quantum numbers now live in the magnetic Brillouin zone. Right, so how do we visualize this? So in the absence of the magnetic field, our Brillouin zone along the K2 direction went from 0 to 1, and then along K1 direction also went from 0 to 1. Now this is still true for the K1 direction after we make this projection, but it is no longer quite true for the TL2. And that's because these are eigenstates of TL2 to power Q, which means their eigenvalues are e to the 2 pi I Q times K2. And therefore, what's effectively happening is that the states within each of these strips will not, which are separated by 1 over Q, will not necessarily be orthogonal. Now, all the other states are guaranteed to be orthogonal. So if you pick a state within this first strip and you pick another state within this strip, it will be orthogonal. That's because they are different representations of the magnetic translation group. But because our zero field Brillouin zone extended up to 1, and our finite field zone will be truncated at 1 over Q, we have actually generated extra states here. And these states will be useful for us. So, so the upshot of this story is that we have to make sure that we orthogonalize the states which we obtained in these images. And for that, what's interesting in this particular problem is that it is not enough to choose this n naught to be 0. We also had to include a set of states with n naught equal to 1 or minus 1. In which case, this gave us not 2Q trial states, but for each K1 and K2 within this magnetic Brillouin zone, but it gave us 4Q states. Now, if we compute the singular value eigenvalues for the overlap matrix, it looks like this. There's a gap. And indeed, we find that there are 2Q orthonormal states that we can get from this trial state, and then the rest are very small. And so now this is the basis that we can use to solve the finite field problem. Okay, and the reason why we needed to include not just n naught equal to 0, but n naught equal to 1 actually is related to the topology of the problem, which I can explain to those who are interested. If this was a topological trivial band, we found that it was enough just to keep n naught to be 0, and then we will also get the correct number of orthonormal states. So now we have a basis. We have a basis at finite field. The basis projects to the Hilbert space we're interested in, and we can take the finite field Hamiltonian, sandwich it in that basis, and compute its spectrum, never using any Landau levels. First thing I should show you, though, is to calibrate this. We actually did solve the problem with Landau levels. And then we ask, how good is the overlap of the projector that we obtain using these hybrid Wannier method onto the narrow band computed at finite field. And what we find is that as long as we are at low field, so this is phi over phi naught, 1 over 10, then most of the support is indeed in the narrow bands, and there's some small spillover to the remote bands. But if we increase the magnetic field, the spillover gets stronger. And this effect is bigger for larger ratio of the AA to AB tunneling than near the chiral limit, where the spillover is smaller. The gap to the remote bands in the chiral limit is also larger, so that's likely the reason why this spillover is bigger when this gap is small. But nevertheless, in the limit of small field, the projector will limit to the projector entirely onto the narrow bands at finite field. So this gives us some confidence that we have the right projector. I should also show you what do the non-interacting Hofstadter spectra look like. We compute them using two different methods. So this is not the magic angle. W0 over W1 here is chosen to be 0.7, which is close to the believed realistic value. And the black dots here are computed using the usual Landau level method. We cannot go to too low of a magnetic field because it's computationally costly, but you see that at low magnetic fields, we get a nice overlap of the spectra using this new method. If we go to the magic angle, the same is true. The method will break down at higher fields for the reason that I mentioned. We get spillover into the remote bands. There's a way to, in principle, there's a way to fix it, but let me just not discuss, so that this will extend further, but let me just not discuss this here and focus only on the low field part. But I think this method is more general than just the low field method. Okay, so now that we are confident that we can get the spectra, we can get the projectors, we would like to solve the problem that I motivated at the beginning, namely the single particle excitation at, in this particular case, charge neutrality point, but in the strong coupling limit at small magnetic field. And one can convince oneself that this commutator trick still goes through at a finite field. And so if this is our creation or annihilation operator, this will still give us a spectrum, except for now we have to project our density fluctuation operator onto the Hilbert space of the narrow bands at finite field. And so that's the zero field spectrum. I remember it was doubly degenerate in the so-called chiral limit, which is in this left panel. The density of states at zero field looks like this, but now the finite field Hofstadter spectrum coming entirely from the Coulomb interactions looks like this from at low fields. So the different color coding here actually corresponds to the states which originated from different Chern bands at zero field. And the interesting thing is that, as you can actually see from this picture, the number of the sublattice, so let's see, so the imbalance in the sublattice polarization reflects the topology of the bands, and in this particular case, the blue is the sublattice A. So we will get more sublattice A polarized states than the B sublattice polarized states. This has to do with the fact that if you took a Chern band and apply an external magnetic field, depending on the orientation of the magnetic field, that Chern band will lose Landau levels or it will gain Landau levels. And that's actually seen in this calculation automatically. So the upshot of this is that we demonstrate that even though the entire dispersion is interaction induced, we still get Landau quantization of these bands. This is the more realistic, believed to be more realistic ratio of the A to AB tunneling. Similar story. The sublattice polarization, though, is not perfect. It's not 1 or -1. It's some fraction of it, but there's still some sublattice polarization which is retained by these Hofstadter subbands. We see that we have the light electrons near the gamma, and the Landau levels formed out of those are shown here. And then from the top, we have the heavy electrons, and these Landau levels are bunched up there. So the spectrum looks physically reasonable from this. We can do the same calculation at filling factor 2 for both the chiral limit and for the more realistic case, either exciting by adding a hole into the problem, which remember I told you inverts the dispersion. So we would get a high density of states at zero field at low energy. In other words, the hole would be heavy at nu equal to 2. And indeed, these Landau levels are bunched up over here. But this part of the spectrum, well, this part of the spectrum is light, and indeed we see nicely separated Landau levels here. Again, the sublattice polarization is perfect there, either perfectly A sublattice polarized or B sublattice polarized. On the other hand, if we excite an electron at nu equal to 2, we find that indeed it goes in as a light electron, which is Landau quantized with a nice separation between the Landau levels. But over here, the Landau levels are bunched up. So in other words, if we were to sit at nu equal to 2 and look physically at the Hofstadter spectrum looking for Landau fans, we would see Landau fans formed out of electrons at nu equal to 2. So these Landau fans will point away from the charge neutrality point. On the other hand, if we're looking for the Landau fans coming from the holes, the cyclotron frequency is too small. So you would not see well-separated Landau fans. And experimentally, this is indeed true. Landau fans point away from the charge neutrality point predominantly in these experiments. Something very similar happens, although maybe it's a little bit more dramatic because these protrusions here and here are stronger. If we go to the more realistic situation, again, we have a heavy hole whose Landau quantization is separated by small effective cyclotron frequencies and the light electron, which have a nice separation between the Landau levels. So how am I doing on time?
Whenever you want.
Okay, so I'm almost done. I have maybe just a few more slides, which we're going to demonstrate the effect that I mentioned, that we are losing states for the Chern plus and for the Chern minus, and then we will be gaining states for the Chern minus zero field states. And there's a way to prove this analytically, but maybe I just won't go through these technical details. But there's a nice way to prove that there's an imbalance between the number of exact zero energy states in the chiral limit at finite field, which are sublattice A and sublattice B polarized. Yeah, so let me just skip this part, and then yeah, skip this part, and then maybe just show you the last part, which is if we are now at mu equal to -4. Where I said we can solve the problem in the presence of kinetic energy as well, exactly, for adding electron into this problem, with a very, very large dielectric constant that we introduced by hand. So basically dial down the Coulomb interaction. We are essentially going to get only the non-interacting dispersion, so 2 Dirac points at the moiré zone K and K prime, with the maximum and the minimum at the gamma point. And then the Hofstadter spectrum in this case is basically the non-interacting Hofstadter spectrum. So we will see the anomalous Landau level coming from these Dirac points. But then over here, we will see nice separation between relatively light mass dispersion here, and they start bunching up as we go closer to the Van Hoff point. And so the idea is now to start increasing the Coulomb interaction. Remember, what happened is that this flattened and eventually inverted as we decreased the dielectric constant, and track what happens to the Hofstadter spectrum. So let me just remind you what happened at zero field. This was the spectrum at zero field. And the corresponding Hofstadter spectrum for that will look like this. So you start with a nice separation between them, and eventually you have these heavy electrons, which have small cyclotron frequencies separating them. So that brings me to the summary. So so I tried to tell you that at the magic angle, the residual interactions within the narrow bands dominate their renormalized bandwidth, and the system is in strong coupling, or at least close to the strong coupling. The dominant correlations induced by the Coulomb interaction within the narrow bands, at least near the integer fillings, are ferromagnetic in this generalized sense. I didn't say much about the group for this rotation being U4 cross U4, but that manifold of states contains these generalized ferromagnets. And what I think is kind of interesting is that the itineracy is naturally generated, even as strong coupling, due to the non-trivial nature of the narrow bands. So the single particle excitations of the strong coupling states disperse, and their bandwidth is itself set by the Coulomb interaction. We found that the single particle excitations in the strong coupling and at finite magnetic field form Landau levels, or more precisely magnetic subbands, which reflect the topology of the narrow bands, because some of them are losing states, some of them are gaining states, without using the Landau levels as a basis. And perhaps this new method will allow finding the Hofstadter spectrum from the zero field hybrid Wannier states without using Landau levels in a larger class of problems, maybe through DFT. So thank you very much for your attention.
I have 2 questions to start off with. So first of all, the Wilson loop, the changes between W0.7 and W00, right? So there's a flat part at 0.7. How does that enter when you go to the magnetic field to the Wannier state?
Not much,
really. I think.
Yeah, I mean,
I would expect
the result
to have an even better basis, because it's basically flat for a large portion of the. Right, so you're not. So that one doesn't have much delocalization.
Right. I see what you mean. I think that's not quite the problem. The problem more physically is that the gap to the remote bands is smaller in that case than in a chiral limit. And so when we apply an external field, we're going to get admixture from the remote bands. Now, why does one get admixture from the remote bands? So let's step back and look at the continuum Hamiltonian. So in the continuum Hamiltonian, we have the Dirac part on the diagonal, and then of course the interlayer tunneling on the off diagonal. So the problem that let's confine ourselves to low field. So at low field, physically, it makes a lot of sense that the you want to solve the problem with the W's first, and then somehow turn on a field on the resulting Hilbert space. But now imagine that you increase the field such that the separation between the lambda levels of the Dirac part of the Hamiltonian without the interlayer tunneling, which is itself going like VF over magnetic length. Now, when that becomes comparable to W's, then it makes no sense to project onto the problem solved with the W's only. And I think that that gets worse if that gap to the remote band gets smaller.
So then you'd solve the problem in B field first, and then
exactly. So exactly. So the idea would be, let's say we solve the problem with lambda levels at half flux. That's cheap because the upper cutoff, it doesn't have to be that large. And then if you want to go near half flux, we would Wannierize the resulting Hofstadter bands at half flux, hybrid Wannierize those. And then project the Hamiltonian for the deviation from half flux onto those hybrid Wannier states and their associated magnetic association group projectors. You see, and so that will bring us close to 1/2. Then if you wanted to solve the problem near 1/3, we could do it near 1/3. So as long as it's a simple fraction, as long as the denominator is not very large, I don't think there is too much advantage to solving the problem with other method than lambda levels. Near zero field is a problem, and I think also very close to such simple fractions. It's better to, in my opinion, to solve with these hybrids. But yeah, I think you're right. I mean, there's this flat part of the Wilson loop, but I think the bigger effect is the gap closing to the remote.
Okay, I can ask a second question, but maybe first let's see if there's other questions.
I'll do one of them.
Okay.
Next. So this is for the zero field part.
Okay.
So you showed how the excitations have dispersion that comes completely from the Coulomb, the projected Coulomb interaction.
Yeah.
Is this a statement you make without including the kinetic part, and then you compare it and you see that it's small, or you include the kinetic part and then? I mean, do you have numbers for this? Once you include the kinetic part, how small is it?
Yeah, so I showed you actually at nu equal to -4, we can do this exactly, right?
Right, this
yeah.
And okay.
Right, and that was not even a magic angle, by the way, that was 1.38. Yeah, so, but let me put the number, let me state the number slightly differently. So say you are at the magic angle and you solve the continuum Hamiltonian. The bandwidth you would get in a non-interacting case is, let's just say 5-ish MeV. The bandwidth that you would get from Coulomb interaction depends on the dielectric constant. But say it's 15 for the electron and 15 for the hole, it's bigger. Now, experimentally, of course, experimentally there are other effects. There's strain, etc. But if you tunnel into the narrow bands while they're empty, compared to when they are partially occupied, there is at least doubling of the bandwidth, if not more than doubling. So I think there's no doubt that the Coulomb interactions have a big effect on the narrow bands. Yeah. Thanks. Go on.
So in your in the nu equals -4 or 4, which is what you showed last, I guess in the previous slide, the Dirac levels seem to kind of last for a long time, even once you get the Coulomb flipping the lower band, right? So I guess so at some point Coulomb flips the lower band and starts getting.
So at epsilon 10, they're still isolated.
Right. But
oops. Okay.
Right, I guess. Yeah, let's
Okay,
just
I
say
don't know how
7
to
or
do
something. Yeah, let's say 7, right?
Okay.
At 7, they still seem to. I mean, they get mixed by the, but.
I mean, this here,
Right.
this 0 on the level.
Right. So they kind of like.
Maybe they get mixed to some of this. That's what you're saying?
Well, they don't seem to, right?
Yeah.
You think they should?
Well, I have no intuition, right?
Yeah.
But it seems like they're very, very separate for like maybe I guess the quantization is larger, right? The gap is larger than this one, right? But I guess from maybe my eyes were not, but I guess I was seeing it even when it goes way up a little bit. Like if you go to epsilon 8 or something, then you still see them, which that was surprising. Maybe exactly.
Now you see, you start mixing it in.
Right.
Yeah. This.
Oh yeah, you start. Right, but that's already right. That's already. You start getting a slope, right? That's the mixture. But there's
I think the blue one was the 0 coming from the.
Yeah, the blue one was the 0, and that still remains 0, right? It's not.
So, would you mean it still is related to the 0 lambda level of the Dirac?
Right.
It's so the Sabati's polarization indeed kind of right. So the Sabati's polarization of the blue tells you it's coming from the Dirac.
That's
Right, exactly. And this one then just comes from, I guess, this.
So that's why it doesn't mix, I guess. That's just polarized, right?
Yeah.
Because you can see them even.
Right. It's a good point.
I see. Okay, cool.
Welcome.
More questions? If not, let's thank Oskar.